So Tony Muscatello has been with the Mars Society since its foundation, and he's also part of our steering committee. And he was previously our steering committee chair, so he's a big part of the Mars Society. And he's going to talk to you today about terraforming Mars and self-replicating robots and oxygen.
I'll just talk a little louder for a moment. As Lucinda said, I've been with the Mars Society since the first year, and I'm member number 70, so I got in the first 100, if that means anything to you. I also just retired from working for NASA at the Kennedy Space Center back in January, and so now I'm a free agent, so that's why I'm listed as a space resources consultant, not NASA KSC. And I'm looking for work, so. And my co-author is Dr. Philip Metzger at the Planetary Science Research branch at the Florida Space Institute, which is associated with the University of Central Florida in Orlando. Phil used to be a colleague of mine at Kennedy Space Center 5 years ago or so. He retired as well and has been working there. And wanted to also mention that this is a work in progress. I don't have all the answers. So you can ask the questions. I don't guarantee I'll have the answers. But I'll give you a little background and talk a little bit more about what Bob Zubrin mentioned this morning and at the steering committee about their CO2 on Mars abundance. And I'll look at some of the problems with previous terraforming technologies and some similar ideas that I discovered about what I came up with. Some of the basics of the self-replicating robots idea, of which I am not an expert, but Phil Metzger knows a lot more than I do about that. Look at oxygen production technologies that could be used and what other Mars resources would be available, and kind of outline the approach and then go through some recommendations. Before we get too much further, I wanted to mention this textbook called Terraforming Engineering Planetary Environments that by Martin Fogg back in 1995. It's the only textbook in the field that I know of, and I highly recommend it to anyone who wants to really dig into the basics of terraforming. It's out of print now, unfortunately, but I did find it on Amazon for $256 used. I forgot to check for eBay, and there might be some out there as well. So as mentioned, Bruce Jakosky and Mr. Edwards came up with this paper that came out. Actually, I came up with this concept before the publication of that, and so I was lucky to have terraforming in the news very recently. Their premises are that only carbon dioxide and water are going to be present in enough quantities on Mars, if at all, to accomplish terraforming. With the limited definition of terraforming in this circumstance, as to make a thick enough atmosphere to go outside. You may need breathing gas, but not necessarily have plants and things like that growing yet. They rejected the idea of making chlorofluorocarbons because they can be destroyed by ozone and ultraviolet radiation and so forth. And it's very difficult to make them with current technologies. And if you don't get enough warming with CO2, water, if you vaporize the water, it'll just freeze back out again because it's too cold. And they looked at potential sources of carbon dioxide, which are the polar caps and water ice clathrate that CO2 can form, CO2 on the regolith and in carbonate rocks. Current atmosphere is only 6 millibar of CO2, which corresponds to 15 grams of CO2 per square centimeter. A little more detail, they figure that there's about 6 millibars of dry ice at the poles, but that the clathrate form is unlikely. As I recall, it was because the temperatures are too high for the clathrate to form under Mars conditions. They say there's about 40 millibar of CO2 adsorbed in the regolith, and that it would take 10,000 years, even if you warmed up the atmosphere, for the heat to permeate into the ground. And then they also estimate about 50 millibar of CO2 in carbonate materials, and estimate you could get about 12 millibar of that, and you have to heat it up to 300 degrees C to get the CO2. And as mentioned as well, about CO2 is being lost to the space, which corresponds to currently 1.5 kilograms of oxygen per second from the upper atmosphere. And they think about up to 90% of the original 1 bar of CO2 based on the carbon-13, carbon-12 ratio observed on Mars. And they figure there's about a total of 20 millibars of CO2 possible that you can get on Mars. And that would be much less, that would be less than 10 degrees Kelvin that you could get warmed. And you need 60 degrees to have liquid water on the surface of Mars. And you need 1 bar to melt the water ice. And the table on the right, I won't go through, summarizes all that. That's in the paper. Robert Zubrin has published on Facebook a rebuttal and he summarized a little bit of it today and quite a bit more last night. Jakosky paper ignores making tetrafluoromethane, which is resistant to UV and does not destroy ozone, can raise the temperature by 10 Kelvin and liberate the ice cap in the soil. You'll get a runaway greenhouse, and you could also make methane and ammonia, which are also strong greenhouse gases. If you have 1% CO2 adsorbed in the soil, and that's 100 meters thick on average, then you would get 300 millibar of CO2, not 40 millibars. Terrestrial minerals can absorb 10% CO2, and it only takes 500 years, not 10,000, to reach thermal equilibrium to get that CO2 off. He did not require that you get carbon dioxide from carbonates in this paper that he did with Chris McKay back in 1993. Jakosky estimates about 20 millibar total CO2, though he listed 400 millibar as possibly being there. And Robert says that makes no sense. And another quote, the Jakosky paper is systematically pessimistic and without foundation. So is there enough CO2 there or not? It's difficult to say for sure right now, but there are various terraforming concepts which require to have a large amount of CO2 already there and available. That, to me, induces risk, and there are alternative methods that we can use. And so I'm going to have to zip through all these. I've got too many slides, but one way was to use nuclear weapons to put dark materials on the ice cap to melt the CO2. You would do that every spring, but this also depends on having rich CO2 Mars availability, and the dust might sink into the ice, and there's all kinds of other problems, such as political issues with using nuclear weapons. Asteroid impactors, the big problem there is that each impact is about equivalent to 70,000 1-megaton hydrogen bombs, so you're going to have quite a bit of damage to the surface of Mars. Oh, sorry. It also takes a very long time to move asteroids and comets and so forth around, decades. And there's also been mention of using self-replicating robots. In this case, 100-kilogram human-sized robots by, I think it was Robert Moll. But you would also, this depends on having a human base there with nuclear power, and the robots would mine the regolith and make aluminum for the major components. But this would be assuming that you already have a thick CO2 atmosphere through some other technology, and you're turning it into oxygen and carbon to create an oxygen atmosphere. So this is different from what I'm talking about. It's also mentioned by, again, Robert under using self-reproducing machines, but he didn't go into details in this particular reference, at least that I found. But writes these off as, at least for now, we don't know how to do this. But if you did have them, they would probably be solar powered, and so if you covered the entire planet with machines doing this and had solar panels doing that, you would get about solar efficiency of 30%. So you need the whole planet's surface. One other reference I found that is actually very similar to what I came up with, I thought was an original idea, but it's not. By Freitas, and the idea is to make a 150 millibar atmosphere, and you need 10 to the 17th kilograms of oxygen. And it takes a lot of energy to make oxygen, and so you need 10 to the 24 joules of energy, and it would take 24 years to make these systems, and then they would be reconfigured to make oxygen. And so it would take either 330 years or less than 100 years if you could increase the capabilities. And you would have to excavate 4 meters of the surface of Mars. And in that process, while you're doing it, you might as well do something useful, so you can make artificial seas, lakes, roadways, subterranean agriculture, greenhouses, or cities. I'm going to skip. It was a very general idea. So what do we do about all this? I think there's room for a modified approach by using self-replicating robots and using oxygen as your major gas, as Freitas said as well. In fact, you wouldn't necessarily have to have people on Mars to start this. You could send the robots that would start building other robots by processing the regolith. And the chemistry of this is fairly well known. And there is some work already being done on self-replicating robots. Something called a RepRap can make a large fraction of the parts to make another RepRap. You have to supply the electronics, it looks like, and maybe some of the metal components. But the concept is there and being developed. Professor Alex Ellery at Carleton University in Ottawa, Canada, has actually been working on this quite a bit in terms of applying it to space applications. Several of his publications, not all of them, and I'll refer to the bottom one. I've done a little work with him, given him some information about the current technologies for in situ resource utilization. There's a journal article that's been submitted, but I can't quote all that yet. The key thing is if you can make an electric motor using 3D printed parts, you're 90% of the way there, because that's the basics of moving stuff around is an electric motor. Study that Phil Metzger, Rob Mueller, Jim Monagani, and I did about 6 years ago, and Phil did most of the work, talks about using self-replicating robots on the moon and various generations of increasing complexity and so forth, and more independent, as was being discussed in the first paper in this session. But you only have to send 8 tons of materials to the moon to get started, and then it starts branching off and duplicating itself and having an exponential growth rate. So you can bootstrap a space industry in a fairly short time for minimal cost and start right away. You don't have to wait for some magical breakthrough. So we need a similar model for terraforming Mars using this approach. We don't have one yet, so that's future work. But something you can say is that exponential growth is is going to be exponential growth. You just keep duplicating, one makes two, makes four, et cetera, et cetera. And so after a while, you're getting thousands and thousands of them and even more. So you can start with a minimal mass and keep going from there. So I think the idea is feasible. There's a lot of work to be done, but probably want to do it somewhat differently than on the moon. Since it's difficult to get a lot of people there, at least initially, you might want to have a base on Deimos or somewhere to operate it. Or, but that would mean you couldn't get started until you have people there. If you could get artificial intelligence at a high enough level, then you could go ahead and have these things run themselves. And I came up with this quote, if we can have self-driving cars on Earth, we can have self-directing machinery on Mars, right? Simple, right? Well, maybe not so simple. Well, current atmosphere is about 7 millibar, mostly carbon dioxide, a couple of percent of argon, nitrogen, and some other things. The goal is to make 300 millibars of oxygen with 20 millibars of CO2, assuming Jakosky is right as a minimum. It could be better than that, but let's just say that, and then you'll have some traces of other things. And the 300 millibars is equivalent to 4.5 psi, and the Apollo spacecraft used 5 psi pure oxygen once they were in orbit and headed towards the moon. And so you can live in that, and things don't burst into flame right away. McKay, Toon, and Casting recommended that same pressure as well, and there's nothing flammable on Mars at the moment anyway, so that's not that, at least initially, a problem. So the surface area of Mars is about 1.5, well, let's see, times 10 to the 14th square meters, which is a lot, equivalent to the land area on the Earth. So multiplying that pressure times the surface area, you come up with, you need 8,000 kilograms of oxygen per square meter. But after you adjust for the lower Mars gravity, you need a taller column of oxygen to get the same pressure, about a factor of 3. So that adds up to 1.2 times 10 to the 15th metric tons, or 1.2 quadrillion tons of oxygen. So if you can make 120 trillion tons a year, it'll take 10 years. If it's 12, then 100 years. So it's a long-term project. So how much oxygen is needed? So McKay et al. Modeled the Earth-like atmosphere, and even if you had that much pressure on Mars, you could, set the temperature at 15 degrees. The figure in the upper right there shows that it's not stable. It's too warm by 70 degrees, and even if you had it that warm, it would cool off over time. So I was surprised at this and disappointed, but facts are facts. So you have to add some fluorocarbons, super greenhouse gases to the mixture as well. You can't do it with just oxygen alone and increased thermal mass that would bring. So in the lower right is a figure from Marinova and McKay showing the infrared absorption in the bars across, and then the infrared emission as a function of temperature of Mars and Earth. So water, yes, is a real great greenhouse gas, but until you get it warm enough, it'll freeze out. Octafluoropropane looks like the best material to use, and that because it absorbs just over most of the spectrum and would help out with the CO2 once you get that released. So how do we make the oxygen? And I'll go quickly through some studies that NASA has done, mainly for the moon, but you can reduce iron oxides, in this case ilmenite, with hydrogen and make water, electrolyze the water and make oxygen, and you'll have iron metal left over. And then you can use either hydrogen or carbon monoxide, and just recycle those over and over again. As you electrolyze the water, you regenerate your materials. And then there's a process called carbothermal reduction, in which you use methane, which can be decomposed at high temperatures into carbon and hydrogen. That reacts with iron, titanium, silicon silicates, and you'll make carbon monoxide and metals. And then the methane gets regenerated using the Sabatier reaction, same as within the Mars direct process of making methane from CO2. And then you electrolyze the water and you get the oxygen. And you can get around 50% oxygen out of the regolith this way. During field demonstration we did on Mauna Kea volcano in Hawaii in 2010, we field tested a carbothermal reduction system with a solar concentrator with a beam of light that went down and melted the regolith. And in the right there, you can see a picture of one of those pucks, about a silver dollar size of material. This one only did one at a time. The design was actually for 6, so you need more solar concentrators. And you got about 10% oxygen out of them, or 10 times as much oxygen this way. Hydrogen reduction is only about 1% or so. And there's also the molten regolith electrolysis process. And you melt the regolith, pass a current through it, oxygen comes off at one electrode, metals come off at the other. And so you can get on the order of 20% there. And there's also a carbothermal reduction process that uses carbon monoxide to first reduce the iron oxides, and then you deposit carbon by disproportionation, and then that does the same sort of carbothermal reduction. And you can see some of the products, Pioneer Astronautics, work by Mark Berggren and Robert Zubrin, and what they've done with that process. Excuse me. So, and there's some more work on that. And this one also worked about 15 to 20% oxygen yield. So I can't go through all of this, but I did a summary of the work. The solar carbothermal reduction seems to me the best choice because it has highest demonstrated production rate with reasonable oxygen yield. And then all these technologies will be also at the same time as you're making the oxygen, you'll be releasing the water and any absorbed CO2 during the heating cycle. Okay, so I will need to wrap up quickly here. We can make super greenhouse gases, but we need to work on that a bit more as to which one. And, but there is a way to do it using cobalt fluoride. And you can get various degrees of warming. But again, we need to work on that some more to figure out exactly how much. We can find metals on Mars, as was mentioned earlier, in the meteorites as well. Those could be a source of fluorine. Well, the meteorites can supply us cobalt and nickel. Fluorine is available on Mars in the form of fluorite. So those are the basic materials. And here's where I got shocked in terms of how much you got to mine. And I got to triple check this. I'm saying we need to dig down to about 100 meters over half the surface of Mars to get enough oxygen, which is way different from what the previous study, Fridas, I think it was, mentioned. So that's going to be a lot of digging. So we don't have models of all these processes. There's some work done for molten regolith electrolysis where you can get 4,000 kilograms a year for a system that weighs 600 kilograms, and needs 20 kilowatts. And that looks promising to me, that if you can get that kind of ratio, more mass out per year than you put into the metal and so forth. Oops, sorry. And then you can take, once the robots are done with making the atmosphere, you can reconfigure them to make other things. So you get enough infrastructure for a whole new civilization once you're done with this. Or you can be building it as you go as well. Well, let me just, so you can do, get a lot of benefits of having an atmosphere. You can fly through it with an airplane. It adds, it'll make ozone, it'll shield the surface from ultraviolet radiation, and give you radiation shielding from solar flares and galactic cosmic radiation. There are lots of questions to be answered about platinum. What do we do about that? Since we need that for electrodes, iridium, if we do a molten regolith electrolysis. Nickel can replace ruthenium for the Sabatier catalyst. I think there's enough power with solar cells, but direct solar energy could be useful as well. And how much metal? Oh, with the direct solar energy, you could also use that to generate electricity with a little steam-powered electric generator. There's dust, just dust storms, as was mentioned earlier, solar flares. What will happen once you have metals in the slag? Are they going to start soaking up the atmosphere? I don't think so, but we need to double check that. Will the plants grow in whatever you left behind? I'm not sure, but you'll destroy the perchlorates at least. So it seems feasible, and I think we can do it. Maybe I'm wrong about 50%, and I would be very happy if it were a lot less of the surface of Earth. But do more around the equator so you have solar power all the time and warmer temperatures. And I think this is the greatest part of this, though, is this is a great topic for students to work on. You could get theses, PhDs, et cetera, working on this. So I'm looking for help on that. And so I have time for a couple of questions, and I'll end with a quote. Who knew terraforming a planet could be so complicated? Thank you.